Hello everyone, welcome to this online course on material science. This is lecture 4 in module 2, and in this module we are discussing the topic the superconductivity. And in this lecture my plan is to explain the Meissner effect, right, which I have introduced in the previous lectures. This effect is also sometimes known as the Meissner ocean field effect. So if you recall, the effect says that the superconductor expels a weak magnetic field. So idea is that if in a superconducting state, the material will not allow any magnetic field in its bulk, right, the interior, it will expel them. So one important thing usually students miss sometimes is that the weak part of the magnetic field. So this effect, when we are talking about this effect, you have to remember the applied magnetic field has to be smaller than the critical magnetic field of the superconductor, because you can see if you raise or crank up your magnetic field above Hc, then the material will lose its superconducting property, right? It will become normal, and then the magnetic field will penetrate right through the material. That's not a problem. So to talk about this Meissner ocean field effect, you have to remember that the magnetic field must not cross the critical magnetic field limit of the superconductor. This is the point sometimes students don't remember. So now in here I will try to explain this phenomena with from electrodynamic arguments, and then I will use some thermodynamic reasons to explain this effect. But in a deep level, to answer this question, why the magnetic field is expelled in a superconducting material, we need at least, if you go to some phenomenological theory, we need the Landau-Ginzburg theory, and then the real microscopic theory of the superconductor, which is the BCS theory, Bardeen, Cooper, and Schrieffer. These three people who explain the microscopic origin of superconductivity. In that model, you can explain everything why the material expels magnetic field. But in this lecture, I will not go into those deep models to explain this Meissner effect. Rather, I will talk about from an electrodynamic perspective and like a phenomenological discussion about why this effect may exist in superconductor. So to start the discussion, let's say we have these three pictures, right? So here in this axis, if you go from this top to down, then the time is flowing, right? So let's say this is your step 1. So in the step 1, what we have here is a small spherical sample, right? So this is our spherical sample, a superconducting material. But if you recall, here the transition temperature is Tc, and at now the temperature of this sample is above Tc. So you can see that here the sample is not superconducting, right? So here sample is not superconducting, right? And also there is no applied magnetic field. So that's how this state is defined. Now later what you do, that you keep the magnetic field still 0, so no magnetic field in this stage, but you go below the superconducting transition temperature. So the sample temperature is reduced, keeping the magnetic field still 0. So now in this step, right, you can see this intermediate step, the sample is superconducting because we are below the transition temperature. Now, once the sample is superconducting, now let's say we apply some magnetic field. So in this step, what we are doing, that here we are applying some magnetic field, right? External magnetic field. External magnetic field B. Now we know that in the superconducting state, right, this is a superconductor because now it's in superconducting phase, the transition temperature is below Tc. We don't have any magnetic field. Why? Because we didn't apply any magnetic field. Now from this stage to this stage, what we change is just we put some magnetic field. So here B is not equal to 0. But you remember that the superconductor has zero resistivity, right? And zero resistivity means the electric field inside the superconductor is 0. Now if the electric field inside the superconductor is 0, then from Maxwell equation, right, you know that curl of E is nothing but negative rate of change of the magnetic field. Now if E electric field is 0, this term is 0. What that means is that the rate of change of magnetic field is 0. It means the magnetic field inside the superconductor cannot change, right? So B is constant. So in the sample was superconducting here, and we didn't apply any magnetic field. So what is the magnetic field inside the superconductor? That's 0, right? Now even if we apply some magnetic field, but keeping that, so in this step you have to remember that the transition temperature, the temperature is below Tc, so the material is superconducting. So from this step to this step, the magnetic field will not penetrate inside the bulk of the superconductor because the magnetic field stays constant. So it is 0 here, it will stay 0 here, right? And the interesting thing to remember that when I say B is a constant in a superconducting material, this constant is 0, not any other value. In a superconducting material, sorry about that, B is 0. That's why we can see that this argument of zero resistivity kind of explain in this series of events where you cool the sample first and then apply magnetic field, right? It explains why magnetic field cannot penetrate, because you cannot change the magnetic field inside a superconducting material. That's due to zero resistivity, and as you cannot change, the zero magnetic field remains 0, but all the magnetic flux line now will go outside and bend along the surface of the superconductor, right? That's kind of explain why Meissner effect is a possibility, right, for a superconducting material. But let's try to change this series of events where now again we have a piece of superconducting spherical sample, right? So again we have a spherical sample, and now you can see in this sample the starting point is always the same, that the temperature of this sample is above Tc, so the material is not superconducting, right? Here remember, not superconducting because the T is above Tc and we are not applying any magnetic field. Now let's apply some magnetic field keeping the T above Tc. So here the first thing to note is that the material is not superconducting yet because T is still above Tc. Now if you apply some magnetic field, what will happen? You can see the flux line is penetrating the material, right? Because the material is not superconducting because the T is above Tc. There is no problem of penetrating the sample above Tc. Now from this step to this step, we keep the magnetic field turned on, but let's say you go below Tc. Now the Meissner effect says that the magnetic field will be expelled, right? So that's why I am drawing this flux line bending and away from the bulk of the superconductor. So the inside there is the magnetic flux line. They will be kind of repelled, right? Now the question is why this is the case? Can we explain this in terms of the zero resistivity, right? We know the zero resistivity term. The answer is no. The zero resistivity effect cannot explain the Meissner effect. I mean, in this sequence, you can explain it from the zero resistivity, where you cool down the sample and then you apply the magnetic field. But in any experiment, you always change the order, right? Here, what you're doing, you're applying the magnetic field first, and then you are lowering the temperature below Tc. In those two type of experiment, you can see the final state is the same. Here the magnetic flux lines are expelled from the interior, and we know why, because the resistivity is zero. Here the state is the same. The magnetic flux lines are like expelled or repelled away from the bulk of the superconductor, but we cannot explain it from the zero resistivity, right? But the end product is the same. The end state of the experiment is the same. So let us combine these two path of the two different types of ordering of the events in the experiment. Like this is one kind of flow, right, where you cool down the temperature below Tc first, then you apply magnetic field. Or you can go in this path where you keep the transition temperature above Tc but apply the magnetic field first, and then you cool down to make the material superconducting. And the idea is that even that we can understand why this is happening, but why the magnetic field is expelled in this path but not really in this path, from the discussion that we have had so far. But you can see the end state of the material is the same regardless of which path you follow. Either you lower your temperature first, then apply magnetic field, or you apply the magnetic field first, then lower the transition temperature below Tc, right? So you can see that the final state, which is the Meissner state, right? This is your Meissner state because all the magnetic flux lines are expelled from the interior, right? So the critical observation is that the final state is independent of the history. Do you understand this statement? History means whether you go from this path or this path, whether you apply the magnetic field later or earlier, the end result is that the magnetic flux line will always be expelled. In one path we can explain from zero resistivity, in the other path even we don't understand, but we know that this is experimental finding that magnetic field will be expelled in superconducting state. So the final state does not depend on which path or how do you reach the final state, right? And when some state does not care about the history or of the samples or the way you performed your experiment, then this is an indication that this Meissner state is a thermodynamic equilibrium state of a superconductor, right? So this is a very deep understanding from thermodynamics that thermodynamic equilibrium is in Meissner state, right? So let's say MS, just to mean the Meissner state. So for a superconducting material, the Meissner state is a thermodynamic equilibrium, right? And that's a kind of like phenomenological explanation that why the Meissner effect is favored, because in thermodynamic equilibrium, that's a stable state of the matter, right? So that's why the magnetic field will be expelled. And this is the reason you can see in this part, you can explain the effect with the zero resistivity, but in this part you cannot. But whether you use zero resistivity or not, the final state is the same. And that's the reason why I have mentioned earlier that rho is equal to 0, which is the resistivity goes to 0, is not really the unique characteristic of a superconductor. The unique characteristics is this Meissner effect, right? Because in this path, the zero resistivity does not need it to explain this path. This path requires something else. So that's why you remember that the resistivity part where it vanishes is not really the unique characteristics of superconductor, rather the Meissner effect or the Meissner-Ocean field effect, which says that in the superconducting state, the magnetic field will be completely expelled. That's like the very unique characteristics of superconductor. And just to give you the idea why this is the case, because there are other material where resistivity vanishes, but there is no Meissner effect. You understand, right? So that's why those are not superconductors. So just saying that, okay, some material where resistivity vanishes under some condition, that's a superconductor. That's not really a right statement. The right statement is that the Meissner effect is the key. Superconductor material will show the Meissner effect, but other materials may show the zero resistivity, which is not superconducting. For example, quantum Hall effect. That's a famous example. So I think I have made this point clear, because many students think that the only characteristic property of superconducting material, as the name is superconductor, means superly conducting, right? So the resistivity has to be zero. That's not really the case. The case is more fundamental, is the Meissner effect. And I hope you understand the Meissner effect is a thermodynamic equilibrium of the superconducting state of the matter. That's why it's more fundamental. And I think that's all for this lecture, and thanks for listening.